Andy, I'm sorry I didn't see your email until what, an hour and a half after you sent it or something. Did
I mean, it's fine. I didn't check my email after that anyway, so I just went to bed. So.
Okay. Were you able to finish the problem?
I think I know the direction to go, so I'm just kind of going until I have another question.
Okay. I will try to pay attention. My days are not very free these days, but I'll try to pay attention to email. And if you send me something, you could also give me a text message or a phone call and say, hey, check your email, just to make sure I know.
Can I get your phone number?
I thought I'd give it to you in the past. Well, yeah, I gave it to you the first day of class, but it's that.
Okay.
Now, granted, I never have my ringer on, so I won't see it when it comes in, but I check my phone a lot more than I check anything else.
Yeah, true.
Okay, and you gentlemen should have seen that I got your test graded. Some of the problems, your solutions were almost identical on everything. So anything I talk about will pretty much be the same for both of you. I want to make sure we go through those problems so that there's good understanding and we move forward, rather than being like, I don't know what I missed. I must have missed something important. So just going over each one quickly. Quantum mechanics is fundamentally different from classical in that it's probabilistic instead of deterministic. And I think both of you got that. It's similar because you're still using the same laws of physics and you're still finding the same types of observables, measuring momentum. Doesn't matter if you're in quantum or classical, you're still doing that. It's doing it in a different way. So that's what I was looking for with that question. On the second one, only one of you got this one perfect. What reason do we have to believe quantum mechanics is correct? Its theory is not built on strong A causes B causes C. It's built on conjecture. De Broglie said everything should have a wavelength. No reason why, just it should, because light does. And then the work of Schrodinger was just saying, well, if it does, then I can work up some physics for a wave equation. But it's still built on that conjecture. And likewise with Heisenberg, he was looking at the observable and saying, how can I organize these observables? It's organizational patterns, not built on theory. So to believe it's true, all we have is, well, it gives us correct answers. Okay, those were the two, philosophical in nature questions. This next one came back to bite both of you. The Dirac notation. The ket is a wave function or eigenvector. So for instance, actually we generally put it like this because G without closing with the X could be in terms of any space. If you close it with X, then it makes it a function of X. But it's representing our function or vector. And a ket is the complex conjugate of the function. Or the, I can't remember the term now, but is the Hermitian transpose. It's the complex conjugate of the transpose if it's written as a vector form. And both of you did not do that in the problem that required it. And so that caused you some stress there. Well, not getting it right. So the bra is the complex conjugate. So bra of G would be G star of X. And so if we put those together, bra F ket G is going to be F star G. And then when you put them together, it has the implied integration. So there's another thing, the implied integration. And then you both nailed this. I think you did. We use it because it's a good, useful shorthand way of writing our equations and problems. So any questions about problem 3 there? No? Okay. I do want to know if even if you think that's not fair, I do want to know. Number 4, you both weren't sure what should be on the left side of the operator. One of you put it as if it was a bra. The other one had put a bra, erased it, and put a little squiggle there instead. I didn't know what to make of the squiggle, but it shouldn't be there. It's the H operator acting on psi gives me the energy eigenvalue times psi. And then the last one for the knowledge problems was explain how a wave function can be converted from one complete set of eigenfunctions into another. You both used the example that I gave you on the equation sheet for a continuous function, which is fine. I did it for discrete. They're the same fundamental thing. One of you used the term Fourier transform. Well, Dirichlet's theorem is basically saying you use a Fourier transform. So that was equivalent to invoking the words Dirichlet's theorem. So I think you both did pretty well on that problem. Then finding the eigenvalues. And once again, you both made the same mistake on this. You did everything fine to get to this, to get the correct eigenvalues. And then you correctly put them in to get these two equations. But then you both said these two equations require that it's 0. That is, that you have your eigenvector is the null vector. But these are actually the same equation. So here in my solution, the upper equation, I solved it for x plus. I called them x plus and x minus. One of you called them m and n. I don't remember what the other one called it. But I did the work to show that these are, in fact, exactly the same equations. And that's the way it should be. Now, it's a good check, but it should be that the last of the equations, if it was a 3 by 3, you would have had two unique equations and one that was redundant, right? Because you forced that the determinant to equal 0, which was forcing that the last one's going to be redundant. So in this case, I only had to look at one equation. And so I have this, x is equal to y times 1 plus root 2. So that gives me some normalization constant times, since x is y plus that, I'm just going to assign y as 1 and x is 1 plus root 2. It's not completely defined because I have a normalization constant. And so then I have to apply normalization. And based on what I've said so far, what is bra of the plus going to be? Okay, so this is the ket for the plus vector.
Okay, so it's the complex conjugate of
right.
ket 1.
The complex conjugate is what I want to make sure I heard. So that's going to be a star, and then the transpose, so 1 plus root 2 is the first one, 1 is the second one. And so for orthonormality, that has to equal 1. And so that's going to give me a star times a times 1 plus root 2 times 1 plus, yeah. If you multiply 1 plus square root of 2 times 1 plus square root of 2, you get 1 plus 2 root 2 plus 2. And then 1 times 1 is 1. So that's your A mod squared. And then to take the simplest answer, remember there's an infinite number of answers because you could have any old phase you want, e to the I, any angle. But the easiest is to choose it real. And in that case, a is just equal to 1 over the square root, 4 plus 2 square root of 2. So that was your normalization constant. Now you go on to the negative case for the negative eigenvalue. And again, you both got these equations correct, but you thought that the two equations were incompatible with each other and didn't do the rest of it. The difference is you have x is now y times 1 minus root 2 instead of 1 plus root 2. So everything looks the same. The normalization constant has a minus sign instead of a plus sign. Is the only difference. And I didn't show it, but what relationship should plus and minus have? What should that equal?
0.
That's right.
Yeah, 0. Just 0 orthogonal, right? Okay.
Yep. So if you do this math, let's ignore the constants out front, because if it's equal to 0, those constants aren't going to matter. And we have 1 plus root 2 times 1 minus root 2, which is going to be the inner terms subtract out, and I have 1 minus 2 plus 1 times the constant stuff. But 1 minus 2 plus 1 is 0. So they are indeed orthogonal. You didn't have to show that, just finishing it out. My process here was pretty simple. Once we had the eigenvectors, I just had to normalize them. That's the only thing that you guys didn't do. The next one, the easiest approach is the one that I did. The easiest approach is first use orthogonality. You do the orthogonality, and you will immediately find A, because you're going to have, and remember, neither of you did this. Neither of you did the complex conjugate, and that's what doomed you. You guys got values that were off by a little bit, like you got 8s here instead of 10s because you forgot to do the complex conjugates. So you have minus I times A plus 3 is equal to 0, which gives you A is equal to minus 3I. And so once we have A, then we just go on and we normalize each one. So vector A bra, vector A ket. I have the C mod squared and 3I1 minus 3I1. 3I times minus 3I is positive 9. And 1 times 1 is, of course, 1. And so 9 plus 1 is 10. Hence we get, it's said to use real, so this one you didn't have to worry about anything else. It's going to be the real one of 1 over root 10. And then the B, bra, B ket, comes out to be almost exactly the same. So you guys showed good mastery of everything in this except for the bra part. Insert joke here. This one here was really funny. You both did it perfectly right and then made statements about crud. But you did it perfectly right. So you got the right answer. So I gave you both 15 out of 15. Neither of you wrote this, but you had it all the way to here. And all you had to do then was say, well, it's commutator of A, B acting on psi. This is minus integral from minus infinity to infinity dx acting on psi. Hence, the commutator is minus integral from minus infinity to infinity dx. So you did that one correct. We learned from the last test. So hopefully for the next test, we'll learn some more, right? Okay, any questions you want to ask?
So, for the eigenvalue stuff,
Yeah.
what is, like, whenever we get the eigenvalues and we get the algebraic equations, find x and y.
Okay, so you're talking about this step right here.
Yes. So, like, what can we do every single time to find what x and y have to be? Instead of just, like, making a guess about it.
Well, I didn't make a guess per se. What I have here is in this case, it was only 2 items. So I'm going to have to combine all but one of the equations. So in this case, 2 equations, combine all but one of them, I have to take one of them. It's always good to check the other one to make sure you're consistent. That would be a way to see if your eigenvalue was wrong. If your 2 equations aren't consistent, then your eigenvalue is wrong. But if your equations are consistent, then you just go on, and these will leave you with one unknown. You find, let's say it was a 7 by 7. Lord knows we're not going to do a 7 by 7, right? But you would have to combine the 6 equations, and so you would get, x1 is equal to all of this times x6, or x7. x2 is equal to all of this times x7. x3 is all of this times x7. You would get all of them in terms of x7. And so then you have one unknown still. So you make your eigenvector. In my case, it only had, in this test case, we only had 2. So I had one equation, and I had x in terms of y. And so then I just randomly assigned y to have a value of 1. And that gives me, I could have chosen anything, but there's nothing easier to use than 1. Well, 0 is easier, but 0 is not going to be correct because it'll give you a null result. And so then I just took this equation, said 1 times 1 plus root 2 is 1 plus root 2. And then I have here my normalization constant. Normalization is going to give me the last value. That's why it didn't matter what I chose, because I have the normalization constant that's going to make it come out right. And so then you apply normalization. Other questions?
On the PHYS, did you just not have any notes for the upload, or did you upload the one that was submitted for my test?
I should have uploaded the one that did it not have notes on it?
No, it just has just the scan of what I wrote.
I think it must be a PDF viewer incompatibility, because I actually checked.
Yeah, that might be why.
I checked to make sure that I graded it using my tablet, and it's another layer on the PDF. And I checked before I upload to make sure I was uploading the right persons with the right commentary on it.
Yeah, that's probably what it is.
If it's not, send me an email or something. I'll try to check myself, but I'm pretty sure it's right. Okay. If you have any other comments, email me, whatever. I want feedback. Even if that feedback is, that was a totally great test. Yeah, that feedback is pie in the sky for a teacher, but, we're going to continue looking at the radial solution. And for today, I put in all of that crazy calculus. I was going to make you do this calculus for a homework problem. I said note to self, put that on the next homework assignment, but then I decided to do it anyway. What did that remind me of something that already slipped my mind, so let's not worry about it. So here is, I think, where we left off. We had our solution U. Remember, U is equal to R over R, right? No, U is equal to R times R. And rho was equal to rho kappa R. It's been so long since we did that, I'm not remembering exactly what these definitions are. And they are, pretty important. So I'm going to look it up here just to make sure that I have those right. We have rho kappa R, that is correct. And U doesn't say where I was looking. Yep, U is R times R. Okay, so those are correct. So what we're going to do now is to put these in. That is to put the equation, the polynomial, into the u equation. And to do that, we have to find the second derivative of u. We did all of this out correctly last class period. So here is the full work on the second derivative of u. Now, after I reviewed this, I was like, why didn't I just put parentheses minus 2 parentheses L plus 1 plus rho plus L times L plus 1. I still don't have a good reason why I didn't do that. I think it would have been shorter to write. What was that?
I think the book did it that way.
Yeah. So now putting the second derivative equal to what we get from the Schrodinger equation here, we have, here's just rewriting that second derivative, and then on the other side what we get from the Schrodinger equation, where we've substituted for u. What comes next is rearrangement. So rearrangement means, okay, first step here is simply changing this from rho to the L plus 1 to rho to the L and putting the other row inside. So the 1 became a row, rho 0 over rho became rho 0, and then 1 over rho squared became 1 over rho. So this middle line, that's the only difference that's been made. Why? Because now it has, this here is exactly the same as this here. So now I'm going to combine everything into one bracket that has all of this stuff times v plus all of this stuff times dv d rho, and then this times the second derivative of rho, v with respect to rho. In order for that to be true, either rho to the L has to be 0, which means rho is 0, or e to the minus rho has to be 0, which means rho is infinity. We already knew that. We found this was the solution, well, it was part of the solution for short wavelengths. This was part of the solution for large wavelengths. We'd already covered this base. What's left is the thing in the middle. Everything inside of this bracket has to be 0 for this to be true. So we're checking that case to find our condition for the function v. Now looking at our function v specifically, it's a power series. And so taking the derivatives, here's the first derivative. Did this last period, right? The j equals 0 term is 0 times stuff. So there's nothing added for the j equals 0 term. So I could have started this at j equals 1, and I would have had the same outcome, same equation. And so what we do is we identify a new j, well, let me put it this way. So I define k as j minus 1, which means that j is k plus 1, and I substitute k plus 1 everywhere a j occurs in my equation. So that's k plus 1 times c sub k plus 1 times rho raised to the k, since k plus 1 minus 1 is k. And then we say, well, what was special about k? Nothing. And so then we say, let k equal j, and change all those k's into j's. The textbook doesn't show the intermediate part, but that's all that's been done, is changing the index. And so the upshot of changing that index is that we have two ways we can write the derivative equation. One that has rho to the j and one that has rho to the j minus 1. The reason for that is for the derivative of v with respect to rho, one term is multiplied by rho. The other terms are not. And so I'm going to want to take the one that has rho to the j minus 1 and use that for this term. And the one that has rho to the j I want to use for this term. So to that end, take the second derivative. This second derivative was simply taken by taking the derivative of this version. So that's where the second derivative equation comes. I took this equation and I expanded it out here. So this one here is term 1. That's all times v. It all has rho raised to the 0th power. There's no rho in that bracket for 1. This second piece I broke into 2 terms. The first one has no rho, 2 times L plus 1. And so for that one, I'm going to use this form. The next one has a rho. So that is taking this plus 2 times minus rho times dv over rho. And because it has a rho, I'm going to use this form for dv d rho. So that I have rho to the j minus 1 times rho gives me rho to the j power. The whole goal here is to get the same power of rho for each term. And then my last term with the second derivative, it has rho, so I'm going to use this form here that has rho to the j minus 1. So if I put that in, here is the equation that must be 0. You notice I numbered the terms 1, 2, 3, and 4. They are not in the same order here. They're not in the same order because I wanted the c sub j plus 1s together and the c sub j's together. So now we just factor the c sub j plus 1s and the c sub j's, move things across. So this here, well, these 2 terms here were moved across the equal sign, so their signs changed. So this was a minus, it became a plus. The 2j became a minus, or minus 2j became a plus 2j. And we have an equation that says c sub j plus 1 times all of this stuff must equal c sub j times all of this stuff. So finally, we divide by this term to get an equation for the coefficients. There's only one independent coefficient. C sub 0 is the only independent coefficient. All the rest of them I build up through this relationship, this recursive relationship. So this is really important to finding the polynomial. Now the next couple slides, I did a little bit different than the textbook, but my way is totally legit as far as I know. Looking at the large radius limit. Now in the large radius limit, we already have a solution in the large radius limit. That was our u for large radius was equal to e to the minus rho. That was our large radius solution. Now we're going to check what happens to our total solution with this polynomial in the large radius limit. This polynomial had better not overwhelm this solution for the large radius limit, or else we have a problem. So in the large radius limit, the highest power, okay, come back to all the way here. In the large radius limit, the highest power of rho is going to be the dominating power. And so the higher the j, the more dominating it is. So we're going to take, for large radius, we're going to start by saying, well, that's going to be effectively in the large j limit for my v function. It's kind of important to understand why we shifted from large radius to large j, because this is in the limit as j approaches infinity. And it's because for large radius, the large j's dominate over the small j's. And in fact, only the highest j really matters, right? So that's what I did here. I took the highest power of j. Well, this is going to be 2 times j plus doesn't matter, plus doesn't matter. Plus or minus doesn't matter. So the numerator is just 2j. The denominator, j plus 1 times j plus 2l plus 2, j times j squared. Well, we can cancel one of the j's, and we have c sub j, 2 over j. Now we're going to take this large j limit and apply it to all of the terms. Is that correct? Well, absolutely not. But is it going to give us an approximation? Yes. So I'm going to say for all j's, c sub j is approximately equal to 2 raised to the j over j factorial c0. That is, j1 is c sub 0 times 2 over j. j2 is j1 times 2 over j, which is going to be c0 times 2 squared over 1 times 2. And you keep going up, you're going to get this form for a high c sub j. Since v is the summation of c sub j, so here I put c sub j, rho to the j. If you just combine like terms, that's c sub 0 summation of 2 rho to the j over j factorial, which is the very definition of c sub 0 e to the 2 rho. And so my v function has the form for large radius of c sub 0 e to the 2 rho, which makes my total u function have the form of e to the 2 rho times e to the minus rho, gives me e to the rho. It was that's where that came from. But that is going to blow up for large rhos. All of this work, all the work in these 2 slides, was to show, oops, got a problem. What is the problem? The problem is I cannot have an infinite polynomial. If it's not infinite, it's not a problem. It's got to terminate. So the only way this can work is if the series terminates. So we come back and say, that must mean that there is some c sub j plus 1 equal to 0. Well, how is c sub j plus 1 equals 0? Since c sub j plus 1 is equal to this equation, when the numerator of that equation equals 0. And so what we do is we define, turn off the auto shapes. N is equal to j plus L plus 1 for the maximum j before it becomes 0. So that means I'm going to have 2n minus rho 0 equals 0. Or rho 0 is equal to 2n. Now, right now, what can you tell me about n? There's only one thing you can actually tell me about its value other than it's defined as when it terminates. What can you tell me about its value? Well, n doesn't have to be 0. It can't be 0 is correct. Doesn't have to be even, I mean. But it can't be 0. But 1 is an integer. L is an integer. We've already determined that from the radial solutions. And j was a summation, so that was an integer. So n must be an integer. So that's what we can say right now is n must be an integer. And n is telling us about the maximum j possible. But this equation here is very useful to us because n is an integer and rho 0 is defined based on energy. Let me just go to where I have these slides because I have all of this stuff in my slides. right? So here's where we ended up, 2n minus rho 0 is equal to 0. But rho 0 was defined as this. It was a big, ugly constant to make our lives easier. And kappa depends on energy. So what we now have is suddenly a quantized energy. Go no further, we have the energy solutions. So I can take this, if I put in the kappa, notice this is inverted because it's 1 over kappa. So that's why this is h bar squared over 2me instead of the other way around. And so I have rho aught is equal to the square root of all this stuff. Well, square both sides, solve for E, and you get this is your energy in terms of rho 0. But since rho 0 must be equal to 2n, then I now have the energy in terms of the quantum number n. So this is just substituting in for rho 0, 2n. I had to look at this like 3 times to get the number straight. Since rho 0 is 2n, then this is minus me to the 4th over 8 pi squared epsilon 0 squared h bar squared 2 squared n squared. If you look at this, 8, of course, is 2 times 4. The 4 and the 2 squared are combined to give me the 4 inside of that square. And so then what's left is this 2. This 2 is the remaining 2 there from the 8. And then the pi squared is inside the square. The epsilon 0 squared is inside the square. The h bar squared is outside the square. And of course, the m stays on top. And e squared is the e to the 4th. So all of the terms are accounted for. Why is it broken up like this? Well, because we like to, okay? So this entire thing in the bracket is energy 1. And so we can say the energy is energy 1 divided by n squared. This thing is equal to the Bohr energy, if you will. It's the ground state energy. For a hydrogen atom. Now I'm going to ask you a question that I never got straight until I was a teacher. What is this energy of?
Energy it takes for a electron to be free of the atom?
This is a correct statement. You have to add that energy to make the electron free is a correct statement. But my specific question was a little more pointed than that. What is it the energy of? What has this energy? That's what I always wanted to say too. That's why I'm asking the question, because I want you to think about this and realize it's actually not the energy of the electron. It is the energy of the atom. It was combining the proton and the electron. You can't have that potential energy without having both. So it's not specifically for the electron. It's of the atom. And so we're going to have different energy levels. We start assigning it to electron because we say, well, first electron comes in here, second electron comes here, and this electron has this energy, and this electron has this energy. But really is an energy for the atom. And we'll have different energy states for the atom. Now coming back to, we got time. I was worried that class is about over, but it's not. Coming back to the meaning of all this. The n was based on the maximum j. But it's not just j max. It's not the n is equal to j max. It's j max plus L plus 1. So now we go to, well, what do we know about the L's? we know that L has to be 0 or greater. So L is any integer 0 or greater. So if L is equal to 0, then I would have N is equal to J max plus 1, right? If L is equal to 1, then N is equal to J max plus 2, and so on. N has to be an integer that is not 0. If N is 0, then, well, if N is 0, then you have no solution, right? Because you can't have, if J max was 0 and L was 0 and 1, you'd have 0 plus 1 is equal to 0 is not possible. So N equals 1 is the minimum possible value. If N is 1, J max is going to have to be equal to 0, and L will also have to be 0. If N is equal to 2, you have either J max is 1 and L is 0, or J max is 0 and L is 1. Either one of those cases, it would add up to 2. And if N is 3, it could be 2, 0, or 1, 1, or 0, 2. So a specific N value amount allows multiple values of L. But notice that the J, which is the number of terms in our polynomial, is moving with the N and the L. So we end up with a relationship that says L has to be 0 or greater, but it has to be at least 1 less than N. So that's where that, you guys have learned quantum numbers, in chemistry and physics, and you know that L has to be between 0 and 1 less than N. Now we have a mathematical solution to give us the Y of it. Right, so we're finding pure math solutions for things that you already knew from other, we learned about the M sub L, the orientation part, and we saw a math reason why M had to be between minus L and plus L. Now we see a math reason why L has to be between 0 and N minus 1. So how does this play out? Well, here is our complete solution. We start with R is U over R, right? I had to look that up a minute ago. Rho is kappa R, rho 0. I'm going to put all of this stuff into my, put the U in here, put the rho in here, and here, and here, and put the rho 0, I don't have rho 0 written there. Put the VP in there, and put the C sub J's in there. It's a big chain of putting A into B, B into C, C into D, D into F. And we get a crazy result. Our R function, it depends on both N and L. Both the N we call the principal quantum number. What does the principal quantum number tell us? We already saw the principal quantum number told us the energy. It's actually, the textbook points out, kind of lucky for us. There are other situations where N and L would both be necessary to tell you the energy. And in fact, when we look at the hydrogen atom more carefully, looking at things we glossed over, we'll find that L does matter to the energy. And M sub L also matters to the energy. So we're going to find there's more to it than what we have right now, but right now, the energy only depends on N. So if you were a general chemistry student, you would believe that energy only depends on N. Right? That's all they learn there. So the radial function depends on N and L, and it's got this great solution. Notice we replace V sub P with this thing here that's called the associated Laguerre polynomial. As you can see, the Laguerre polynomial and the associated Laguerre polynomials are just as fun as the, now my mind's gone blank. What were the P, we had the Rodriguez formula and the, Legendre polynomials. Just as fun. I don't know why people come up with these things, but they do. We have to ask Christopher because he's going to be a mathematician who will come up with his own The Tron polynomial.
Like easier now.
Well, in some sense, this makes it easier because we can find the polynomial, any one of the polynomials with these, quote, simple rules. Yes, just like we have simple problems on your test. So the complete approximate wave function is, I am never going to put this all together in one equation. Right? It's pretty complicated. This here is your spherical harmonic. This here is your radial function. These are both normalized. So here you have the normalization constant for the radial function, and here's the normalization constant for the spherical harmonic. So you multiply those two together, and there you have it. Are you feeling good and accomplished?
Just one question.
Go ahead.
Just one. Where did the A come from?
Where did the A come from? That's a really good question. You know, funny thing, I must have spent 30 minutes last night thinking, where does it come from? Looking back. And then I realized one word, defined. If you look, okay, where is it? It's after, here we go. If you look on page 150 of the textbook, he says, combining equations 4.55 and 4.68, we find that kappa equals this stuff, where it doesn't even say the word. It has A, 3 lines, 4 pi epsilon 0 h bar squared over me squared. But what do those 3 lines mean?
Where? Define.
In the box on page 4.72, or on page 150, equation 4.72. It means defined. So A here simply appears because we're defining A is equal to this stuff. And we give it a name, the Bohr radius, which I think is left to a homework problem to show that that is the Bohr radius. And then it says in the subscript 15 that traditionally you actually put A sub 0, but he finds that cumbersome, and so he didn't put the 0. So that's a really good question. Where does the A come from? It's just a shorthand way of writing 4 pi epsilon 0 h bar squared over me squared, which we don't want to write, because this would be an even longer equation if we did. So, just one question. Do you understand it now? I thought that he had done something to derive the Bohr radius here, and I was like, there's been nothing to do to derive the Bohr radius. Then I realized it's defined. So now we're going to go to this website for our last 2 minutes, assuming I get there before 2 minutes is over. Orbitron. Orbitron is a very cool website. I should have loaded it up beforehand, but you know I didn't. Orbitron, let's do Sheffield just to make sure we get the right place. You don't have to do the search more than once. If you haven't been here, you should have. If I misclicked, well, that's my fault. What? Seriously, how hard should it be to click a link? Click that one instead. Is it gonna? Of course not. Let's go straight to the 1S, see if that works. Okay. There is something wrong with my stupid tablet. Copy link address. Paste the link in here. That's the right link. Try a different web browser. It worked perfectly on my computer at home. Come on, Microsoft. You don't have to kill me, man. You can see that I've never used the browser before, and they're really irate about that. Seriously? Microsoft.
If you go back to Microsoft at the bottom, I think it might be doing the same thing. It might be wanting to download
You think so?
or save. I don't know, I can't really see.
Do you want to do, what do I want to do with it? You're right. Yeah, I hit open. I'm going to open an Internet Explorer. See what that does. This is ridiculous. Well, that website should work, and it's really cool. And anyway, I'll figure out why it's not working on my tablet. We know who to blame, though. Microsoft made the tablet. They made the operating system. They made one of the two stinking browsers. It worked perfectly last night when I was preparing for class. It is a cool website. Go to it on your browser. What it allows you to do is to see the things that go into making your orbitals. And I'll explain it next class period unless I truly can't get it to work on the tablet. All right. I'll see you guys Friday.